Gluconeogenesis. So, what does that exactly mean? Well, literally, it means glucose made from the beginning, made new from the beginning. So, we are making glucose from non carbohydrate precursors. So, why does it happen? Well, when your blood glucose drops, right? We've talked about ways that we can remedy this low blood sugar. We've talked about two top-down approaches, right? We can break down our internal stores of glycogen to generate G6P, or we can consume carbohydrates and break those down, bring them in from the GI tract, and have glucose kind of be remedied in that way. But the third way that we can remedy is this bottom-up approach by taking non-carbohydrate precursors and making them into that critical glucose. So I want to make sure to highlight here this important piece that we've got here, that fats cannot be made into glucose, right? Fats cannot be used to make glucose. Well, let's clarify this. Fats are worth a lot of money, and they can actually provide the cost for something that is much more costly, which is glucogenic amino acids. Okay, glucogenic amino acids, if they're able to be made into a pyruvate skeleton, then we can use those for gluconeogenesis and make glucose. So, glucogenic amino acids can be made into glucose, but that's very costly. Fats can pay the cost for that. So there is sort of a place for fats in gluconeogenesis, but it's really only paying the energetic cost. Okay, so how does gluconeogenesis happen? Well, gluconeogenesis is really glycolysis run in reverse, okay? 10 steps of glycolysis, and let's go ahead and remind ourselves and highlight what the 3 steps in glycolysis that were far equilibrium. So I'm going to zoom in here so we can see these a little bit more clearly. We've got the first step, we've got hexokinase, okay? So the first step of glycolysis was a far equilibrium reaction. The third step of glycolysis was a far equilibrium reaction, right? So this is step 3. Importantly, this was the rate determining step. So the rate determining step of glycolysis with phosphofructokinase, PFK. And then the last step of glycolysis was a far equilibrium reaction, right? Pyruvate kinase, so step 10. Right, remember when we learned this in glycolysis, we sort of discussed the fact that these were far equilibrium reactions, which made them good potential control points. Okay, but we highlighted that the 10th step was not going to be a likely good control point. And the first spots, those are always great points to sort of control flux, but not if something feeds in or out after that pathway. And in this situation, specifically with glycolysis, because G6P is such an important branch point metabolite, we cannot control at hexokinase because so much feeds in or out of glycolysis at G6P. So that third step, PFK, that is going to be the important rate determining step. Okay, so remember when we talked about thinking about sort of how we control flux, right? We are thinking about large negative delta G values that are going to be good flux control points. So large negative delta Gs, these are going to be what we have for flux control points. And so for glycolysis, it's steps 1, 3, and 10. So if we want to reverse, we can say that gluconeogenesis is really glycolysis run in reverse, but what we really need to think about is it's all steps but 3 run in reverse, because if we have a step that has a large negative delta G and we want to reverse it, we have to have a different path. So a different path, which in this case means a different enzyme. And importantly, one of those paths must have the input of energy. So one path must have the input of energy. And as we're going to see, that's in the form of either GTP or ATP. So let's revisit sort of glycolysis and sort of talk about what we see here, right? We had hexokinase. That was the important far equilibrium step going in the glycolysis direction. So we are going to see G6Pase be the different enzyme running in reverse and highlighting one of these steps must require the use of energy. It's actually the ATP that is used in hexokinase. So that's where the energy input is. So it's actually a readily downhill reaction to snip off that phosphate. Remember, we talked about when we need G6Pase. When we've broken down, let's say, glycogen in your liver and we've got G6P, we need to export that out to the bloodstream. G6Pase is going to be necessary because only free glucose is exported out into the bloodstream. Okay, so then we've got PFK. We've got PFK here as the rate determining step for glycolysis. So, not surprisingly, the component to this is going to be the rate determining step for gluconeogenesis, and this is FBPase. Okay, so this is the rate determining step for gluconeogenesis. So that sort of system, that small substrate cycle, PFK and FPBase are going to be the rate controlling steps determining flux through both glycolysis and gluconeogenesis. Okay, now we're going to come down to this last part. So pyruvate kinase. So pyruvate kinase down here is the very far equilibrium last step of glycolysis, generating pyruvate and our last ATP. Oh, let me come back up here and remind ourselves, yep, here was the input of energy that we had there. Remember, 1/2 of that substrate cycle has to involve the input of energy. So this last step is a little bit muddier. This is where we're going to spend a little bit of time here sort of talking about something. It's going to introduce a new important branch point metabolite that we'll revisit even more in our citric acid cycle learning unit. But we've got pyruvate kinase here that's responsible for that last far equilibrium step in glycolysis. And reversing it, it's not just one enzyme in one step, but it's 2 enzymes. We're going to see the enzyme pyruvate carboxylase, and we're going to see the enzyme PepsiK. That's how we say both of those. So pyruvate carboxylase, again, we're going to call this PC, okay? And then PepsiK, we call this, like the soft drink, PepsiK is how you sort of pronounce that. And we're going to see that it is this kind of component pathway that requires not only the input of ATP, but we're going to see the input of GTP in the second step. So in another video, we're going to take a little bit of a deep dive as to the chemistry that happens with both of these steps. But one of the things to highlight now is the fact that pyruvate carboxylase is only found in the mitochondria. And that poses a problem, right? Because glycolysis is a cytosolic process. So glycolysis, occurs exclusively in the cytosol. So all the rest of these enzymes live in the cytosol. But pyruvate carboxylase only lives in the mitochondria. So we're going to have to think about some interesting things for how we manage that. Particularly, one last piece to sort of have on this slide, we'll expand on it in another slide, is that there are no transporters. So no transporters for oxaloacetate. That's going to be an important branch point metabolite that we'll expand on in our citric acid cycle learning unit. So let's see if we can sort of process this for a second. We've got pyruvate that can be only made into oxaloacetate using a mitochondrial enzyme called pyruvate carboxylase. But then we have to finish the rest of the gluconeogenesis process by reversing glycolysis enzymes in the cytosol, but there's no transporters for oxaloacetate to get it from the mitochondria where it's made out to the cytosol where the rest of the enzymes for gluconeogenesis are. So how do we manage that? Again, another video is going to walk through these different sort of transport options that we have, often disguising a molecule as another molecule in order to use a transporter that is present for that molecule. So oxaloacetate, really important branch point intermediate. I'm going to take just a minute here and walk through some structural details about some important things to think about with what we have here with oxaloacetate. So first I'm going to start here with pyruvate. So looking at the structure of pyruvate, right, here's pyruvate. Now, what we really want to be able to do to make phosphenylpyruvate is make this carbon atom be nucleophilic. So see if you can follow this logic here. So this carbon atom, change my colors here, we want this carbon atom to be nucleophilic. Because if we think about what we ultimately want to do, we want to make pyruvate into phosphenylpyruvate. So here's the structure of phosphenylpyruvate. Okay. There's phosphenylpyruvate. So what we really wish happened is this carbon atom to be a nucleophile. If it's a nucleophile having a negative charge, we'd likely have those electrons pushed through and resonance stabilized through this adjacent carbonyl oxygen there. And so if we really have deprotonation making this guy a nucleophile, effectively we're having that oxygen be nucleophilic, and then we can do some chemistry with the gamma phosphate of a nucleotide triphosphate, ultimately adding the phosphate up to that oxygen and getting to phosphenylpyruvate. So that's the net of what we're going to do, but it's going to be a two-step process to get there. So see if this makes sense here. This is going to be a common theme that we're going to see. What we have here is an alpha keto acid. Pyruvate is an alpha keto acid. So one of the things that we'll see in another sort of discussion about options for things we do with pyruvate is we can do decarboxylation of that. Okay, we can do pyruvate decarboxylation chemistry. One of the things we're going to see is when we have alpha keto acids that we need to decarboxylate, what we're going to need to do is incorporate a B vitamin. So we're going to revisit that in a little bit here, but this alpha keto acid also has a acidic alpha carbons hydrogen, right? And for the same reason here, we are going to be able to take, and if we deprotonate this, we can push those electrons through to stabilize in that carbonyl's oxygen. Okay, that's why it's mildly acidic. Now, not acidic like a carboxylic acid, right? But acidic enough that what we're going to do is generate something that's nucleophilic. Okay, and what we're going to do is we're going to add it to carbon dioxide. So carbon dioxide here, and as we're going to see on a future video, this is actually going to be in the form of bicarbonate. Okay, but we know that carbon dioxide is a good electrophile. And what we're going to do is we're going to basically be adding CO2 onto this terminal carbon, and we're going to get oxaloacetate. All right, so there's the CO2 that we added. There's the CH2 that was a nucleophile, so let's kind of go ahead and label that this was our CO2 that was here. This is our carbon atom that we had act as a nucleophile, and then here's the rest of the molecule. Okay, so this is oxaloacetate. Oxaloacetate, abbreviated OAA. Okay, so what's going to happen here? Oxaloacetate is a beta keto acid. Okay, what we know about beta keto acids is they easily are going to decarboxylate. Okay, so see if you follow this logic here. I've got these lone pairs of electrons on this oxygen coming down to form a double bond. Okay, and then we're going to put those electrons back here. So it might seem like we just kind of went totally in reverse because now we're going to be removing CO2 and making that nucleophile, but the idea is that we're making that nucleophile in a very potent, usable form. So this is going to be a biological trick we're going to see often, is we're going to carboxylate something to make a beta keto acid so that we can, in a subsequent step, decarboxylate it and make that nucleophile to do something else with it. So what we're going to do then is we're going to be able to take GTP, and that's going to provide that phosphate that we're going to have here. So we're going to have nucleophilic attack on GTP, on that gamma phosphate of GTP. We're going to look at that structurally in just a little bit. And that is going to be how we ultimately add that phosphate up on top. Okay, so even though gluconeogenesis has essentially 11 steps, 9 of them are pretty easy to see as reversals of glycolysis enzymes, right? These are 2 phosphatases that are pretty easy to just understand the chemistry that they do. We're going to focus the bulk of our time over here in this reversal of this last step when we think about pyruvate carboxylase and then PepCK.